A silent cartography of the cosmos has already begun. The vast emptiness of our solar system is being meticulously charted not by giant telescopes, but by swarms of microscopic machines known as asteroid beacons. These tiny explorers are carving detailed maps of asteroids, turning anonymous rocks into characterized assets. By the end of this, you will understand how this invisible network is fundamentally rewriting the rules of space exploration, resource gathering, and even planetary defense. How can machines the size of a grain of rice perceive the internal structure of a mountain floating in the void? And what does it mean for our species to administer the solar system instead of merely exploring it? What do you believe is the ultimate consequence of making the entire cosmos a known and navigable space? The silence of deep space holds a profound and practical problem. How do you map 1 trillion points of interest with only a handful of expensive, fragile spacecraft? The answer did not arrive in a single flash of genius, but grew slowly from two converging and undeniable pressures. The first was the immense economic promise locked within asteroids, mountains of platinum, iron, and water drifting untouched. The second was a far more sobering reality, the existential need to know which of these mountains might one day be on a collision course with Earth. You cannot mine what you cannot find, and you cannot deflect what you cannot see. This dual imperative forced a radical shift in thinking. Instead of building bigger and more complex orbital telescopes, a group of visionary engineers began looking down at the ground, at systems like ant colonies. A single ant is nearly blind, but a colony can find food, build complex structures, and defend itself with stunning efficiency through sheer numbers and simple, shared communication. This biological inspiration sparked the first serious proposals for a synthetic ant colony in space, a swarm of thousands of tiny, identical probes, each one simple, cheap, and disposable, but collectively forming an intelligent sensor network. As the physicist Dr. Aris Thorne once remarked, we are learning to see with 1,000,000 tiny eyes instead of straining with one giant one. The earliest concepts were confined to scientific papers and conference rooms, dismissed by many as pure science fiction. The technological hurdles seemed insurmountable. How do you power something the size of a postage stamp? How do you give it enough intelligence to navigate? How do you get 1,000,000 of them to their destination without bankrupting every space agency on the planet? But the core idea was too powerful to ignore. Small, targeted research grants began to appear, funding the development of microthrusters, miniature spectrometers, and swarm communication protocols. These were not missions yet, they were puzzles. Teams of engineers would take one tiny piece of the problem, like power, and spend years testing microscopic solar cells or harvesting energy from an asteroid's own weak thermal emissions. Slowly, piece by piece, the impossible engineering challenge began to look like a very difficult but solvable problem. This quiet, persistent work in laboratories around the world set the stage for something far grander than a new satellite. It laid the foundation for an entirely new sense, a form of spatial intelligence that would allow humanity to feel the texture of the solar system for the very first time. The true marvel of these beacons is not their collective intelligence, but the microscopic universe of technology packed inside each one. Each unit is a self-contained laboratory, a spacecraft shrunk down to the size of a grain of rice. This was only possible through a revolution in micro-electromechanical systems, or MEMS. Think of MEMS as the art of carving machines out of silicon. creating tiny moving parts and sensors on a scale smaller than the width of a human hair. It is this technology that gives the beacons their senses. A miniature spectrometer, small enough to rest on your fingertip, can analyze the reflected light from an asteroid's surface and determine its elemental composition, identifying veins of platinum or deposits of water ice. Tiny microthrusters, no larger than a dust speck, use minuscule pulses of gas or ions to nudge the beacon through the void, allowing it to hop across an asteroid's surface or maintain its position. And perhaps most crucially, a quantum communication chip enables each beacon to send its data back to a central relay using entangled particles, a method that is both secure and incredibly energy efficient. The engineering challenge was not merely about making these components small, it was about making them tough. Space is a brutal environment, with temperatures that swing from searing heat to deep cold in minutes, and a constant bath of radiation that can fry delicate electronics. Each beacon is essentially a tiny fortress, hardened to withstand these extremes so it can do its job for years on end. This foundational leap in miniaturization is what makes the entire network possible, transforming a visionary idea into a fleet of millions of silent, waiting sentinels. Yet a single beacon, for all its microscopic genius, is nearly blind and powerless on its own. Its true strength does not lie within its silicon shell, but in its connection to thousands of others. This is the second principle, the power of swarm intelligence. Picture not a fleet under central command, but a cloud of gnats swirling around a tree. No single gnat knows the shape of the tree, but the cloud as a whole envelops it perfectly. This is how the beacons operate. They run on decentralized algorithms, a set of simple rules each unit follows. A beacon might only communicate with a dozen other beacons closest to it, sharing its own tiny data set, its position, a reading of the rock beneath it, its trajectory. From this constant, localized chatter, a grand picture begins to form without any single beacon ever understanding it. This emergent intelligence allows the swarm to accomplish what no single probe ever could. If a beacon encounters a deep crater, its simple programming might tell it to signal others to avoid that area, effectively mapping the obstacle through collective avoidance. They spread out to cover vast, irregular surfaces with an efficiency that would be impossible to pre-program from Earth, millions of miles away, and this system is beautifully redundant. If one beacon or 100 fail because of a micrometeorite impact or a component flaw, the swarm simply recalibrates. The map continues to be drawn, the network persists. This collective mind, born from countless simple interactions, is what truly carves the silent map of the void. But how does this distributed mind actually perceive the asteroid it surrounds? The answer lies in a method so subtle it borders on the imperceptible. This silent mapping is achieved through a masterful combination of listening and whispering. The beacons employ two distinct modes of perception, passive and active sensing, to build their detailed portrait without creating a racket. Passive sensing is the art of pure observation. Each beacon acts like a tiny, patient astronomer, simply watching the asteroid it rests upon. It analyzes the faint sunlight reflecting off the dusty regolith, measuring the albedo, which tells scientists how bright or dark the surface is. It also senses the natural heat radiating from the rock, the thermal emissions that ebb and flow as the asteroid spins in and out of sunlight. From these quiet observations, the swarm can piece together the basic shape of the world, its surface temperature variations, and even clues about its composition, all without ever making a sound. But to see beneath the surface, the beacons must occasionally break their silence, though they do so with incredible discretion. This is active sensing. A beacon might emit a single, low-power pulse of laser light, a photon whisper, to measure the exact distance to another part of the asteroid, building a super-precise topographic map. Or it could send out a specific, low-energy radio wave designed to penetrate the rock and bounce off internal structures, revealing cracks, voids, or layers of different density. Think of it like a doctor using a tiny, precise tap to check your reflexes rather than a loud hammer. Every active signal is crafted to be as minimal and focused as possible, a fleeting murmur lost in the background noise of the cosmos. This dual approach is what creates the comprehensive map, from the chemistry of the surface to the hidden architecture within. It allows for this profound act of discovery to remain, for all intents and purposes, a secret. The asteroid gives up its truths without ever knowing it is being watched, a crucial feature for science that requires an untouched environment, and for any future where knowing a resource exists is a strategic advantage you may not want to share. Building billions of these microscopic sentinels requires a manufacturing process that mirrors the scale of the task itself. We are not talking about assembling delicate instruments one by one in a clean room. This is a production revolution, one that takes its cue from the most prolific manufacturing system humanity has ever created, the semiconductor industry. Imagine a facility where vast, silent machines work in darkness, using beams of light to etch intricate circuits and sensors not onto flat silicon wafers, but into three-dimensional forms. This is advanced three-dimensional nanolithography. It is a form of printing that builds structures layer by vanishingly thin layer, creating the complete internal architecture of a beacon, its micro-thrusters and quantum chips, all in a single, continuous process. The raw materials are equally ingenious, starting with abundant silicon but blending in specialized polymers that are incredibly resilient to temperature swings, and even metamaterials, substances engineered to have properties not found in nature. These metamaterials might be designed to passively deflect radiation or to convert the faintest ambient heat into a trickle of electricity. The ultimate objective is a staggering reduction in cost. The vision is a unit price so low that it becomes comparable to a piece of laboratory glassware. At that scale, losing 1,000 beacons to a micrometeorite shower or the harsh radiation of a solar flare is not a mission-ending disaster. It is a simple, budgeted line item. This economic transformation is what finally unlocks the asteroid belt. For the first time, the cost of mapping 1 trillion unknown worlds drops below the immense value of the resources and security that map provides. But once you have produced 1 billion tiny explorers, how do you possibly deliver them to their distant destinations across the solar system? Movement through the void demands a form of propulsion as miniature as the beacons themselves. These are not the roaring engines of science fiction, but silent, patient systems that trade raw power for exquisite efficiency. For the long journey from an orbital delivery pod to a target asteroid millions of kilometers away, many beacons deploy gossamer-thin solar sails. These are not solid sails in the traditional sense, but surfaces thinner than a soap bubble, designed to catch the gentle but constant pressure of light photons streaming from the sun. This provides a continuous, fuel-free thrust, a whisper of acceleration that builds over months and years to guide the swarm across the gulf of space. Once they arrive at their destination, more precise systems take over. Miniaturized ion thrusters, smaller than a pinhead, eject tiny streams of charged atoms, creating a thrust so slight you could not feel it on your skin, but enough to nudge a beacon into a stable orbit or allow it to hop across the asteroid's surface. For the most delicate maneuvers, such as landing on a specific mineral vein, simple cold gas thrusters are used. These release brief, controlled puffs of an inert gas, like a microscopic cough, providing the pinpoint control needed to settle onto dust-covered rock without bouncing back into the void. Guiding these tiny travelers requires an equally ingenious form of navigation, one that functions entirely without external signals like GPS, which simply does not exist beyond Earth. Each beacon carries a star tracker, a tiny camera and processor that constantly looks at the constellations. By recognizing the patterns of familiar stars, it can determine its own orientation, much like an ancient mariner using a sextant. This is combined with onboard gyroscopes that sense even the faintest rotation. But the most crucial element is the swarm itself. The beacons are in constant, low-power communication with their neighbors, sharing their own positional data. Through this endless chatter, they perform a form of collective triangulation, each beacon using the known positions of its siblings to calculate and refine its own location within the cloud. This creates a self-correcting navigational mesh, a living, breathing coordinate system that blankets the asteroid. If one beacon's thrusters fire a fraction too long, sending it slightly off course, the network detects the anomaly, and the surrounding beacons adjust their own positions to maintain the overall formation. This allows the entire swarm to hold its shape and continue its mapping mission with astonishing accuracy, all while drifting through millions of kilometers of empty space, completely autonomous and self-aware. The deployment of a beacon swarm is a logistical ballet, a carefully orchestrated sequence of events that transforms a dormant cargo into a living, sensing cloud. This entire operation begins with the Hive ship, a specialized carrier vessel that serves as a mobile launch platform and interplanetary ferry. Its design is purely functional, a skeletal frame containing thousands of individual launch tubes, each cradling a dormant beacon. The journey itself is one of profound patience. The Hive ship is launched from Earth or an orbiting station onto a precise trajectory, a long, arcing path calculated to intersect with a specific asteroid belt or a solitary near-Earth object. For months or even years, it cruises silently, its precious cargo waiting in the dark. The critical moment arrives not with a roar, but with a series of soft, mechanical clicks. Upon reaching the calculated insertion point, the Hive ship begins its release sequence. It does not eject the beacons in a single, chaotic burst. Instead, it uses precisely timed charges to gently push them out in coordinated waves, a slow-motion blossoming of microscopic explorers into the void. This initial scattering is a delicate and vital dance. Each beacon immediately awakens, its tiny micro-thrusters sputtering to life with minute puffs of cold gas. They do not fly randomly. Their simple algorithms command them to push away from their neighbors, to disperse into a vast, predefined formation that will eventually envelop the target. This dispersal is meticulously timed with the orbital mechanics of the asteroid itself. Engineers back on Earth calculate the release to ensure the cloud's expansion perfectly matches the rock's rotation and path, allowing the swarm to fall into a stable, surrounding orbit with minimal energy expenditure. This flawless initial deployment is what sets the stage for everything that follows. It provides the raw, organized material from which the swarm's collective intelligence can emerge, transforming a million individual specks into a single, unified instrument poised to begin its long, silent watch over a new world. A beacon drifting in the perpetual shadow of a crater rim faces a profound challenge. How does it power its delicate instruments when sunlight is a distant memory? This is where the fifth principle comes into play, the silent art of energy harvesting in the void. For a swarm to function for years, even decades, it must become a master of scavenging, drawing power from the most meager of cosmic offerings. Some beacons, those fortunate enough to operate in sunlit realms, are clad in ultra-thin, high-efficiency solar cells. thinner than a human skin cell that capture every possible photon. But for those destined for the dark or for missions spanning generations, more ingenious solutions are required. One of the most reliable is a miniature radioisotope thermoelectric generator, a tiny RTG. This device contains a small pellet of a radioactive material, safely encased, which steadily decays over decades, producing a constant, gentle heat. A thermoelectric converter then transforms that relentless heat directly into a trickle of electricity, a whisper of power that is enough to sustain the beacon's core functions through the long, cold night. Other designs are even more subtle, acting as cosmic scavengers. They might deploy microscopic grids to catch trace particles from the solar wind, or use their own structure to exploit the weak thermal gradient between their sun-warmed side and their frigid, shadowed side. This minute temperature difference, just a few degrees, can be enough to generate a tiny voltage. It is this relentless, low-level ingenuity that allows the network to persist. The maps they create are not static, one-time snapshots. They are living documents continuously updated, reflecting shifts in an asteroid's spin, fresh crater impacts, or seasonal outgassing. This persistent awareness transforms the asteroid belt from a collection of anonymous rocks into a dynamic, monitored system, a neighborhood under a constant, quiet watch. The final map is a whisper of pure information, a composite portrait built from countless tiny observations. Think of it not as a single image, but as a stack of transparent layers, each revealing a different secret of the asteroid. The foundational layer is a precise gravitational map. By tracking how the entire swarm of beacons subtly wobbles and shifts in its orbit, the network can measure the asteroid's gravity field with incredible detail. These minute variations reveal hidden mass concentrations, dense cores of nickel-iron, and vast, empty caverns lurking just beneath the surface. It is like holding a closed box and, by feeling its weight shift in your hands, being able to pinpoint exactly where a lead weight or a ping-pong ball is hidden inside. Layered directly over this is the mineralogical map. Each beacon's tiny spectrometer has been analyzing the color of sunlight reflected from the dust and rock, creating a sprawling chemical fingerprint of the entire surface. This data paints the asteroid in a rainbow of economic potential, highlighting vivid splotches of water ice frozen in permanent shadows, glittering veins of platinum group metals, and broad stains of rare earth elements essential for modern electronics. A third critical layer captures the object's rotational dynamics. The swarm meticulously tracks the asteroid's exact spin rate, its wobble, and its tumbling motion through space. For a future mining operation, this information is as vital as the location of the metals themselves. You need to know how the asteroid is spinning to safely dock a spacecraft, to deploy anchors, and to calculate the forces any equipment will face. This composite data tapestry transforms an anonymous rock into a fully characterized asset. It tells a scientist about the solar system's formation, and it tells an industrialist about trillions of dollars in raw materials. But this act of revelation immediately raises a profound and difficult question. When a swarm of machines can silently map a celestial body and define its entire economic potential, who does that map truly belong to? This silent network solves its greatest challenge not with a shout, but with a whisper that defies the very nature of space and time. Transmitting critical data across millions of kilometers of void is a monumental task, one where even light itself seems slow. A conventional radio signal from the asteroid belt can take tens of minutes to reach Earth, a delay that renders real-time response impossible for something like an impending asteroid deflection or a time-sensitive mining claim. The solution emerges from the bizarre and beautiful rules of quantum physics. At the heart of this communication system are quantum entangled particle pairs. Imagine two photons created together, linked in such a way that whatever happens to one immediately influences the other, no matter the distance separating them. This is not science fiction, it is a proven phenomenon. Each beacon carries one half of such an entangled pair, while its twin remains secured in a central receiver, perhaps on a hive ship or a dedicated satellite in a stable orbit. When a beacon makes a critical discovery, it does not broadcast a radio wave. Instead, it performs a specific measurement on its entangled particle. That act instantly forces the twin particle light years away into a corresponding state. This change is the message, a single bit of information transmitted faster than light, a silent click in the fabric of reality. The bandwidth of this quantum channel is incredibly narrow. It is a communication straw, not a fire hose. It cannot stream video or vast data files, but it is perfectly suited for sending the most vital, pre-agreed-upon signals. A single, instantaneous quantum click could mean platinum deposit confirmed at grid 7. Another might signal trajectory anomaly detected, collision probability rising. This ensures that the most important alerts, the ones that demand immediate human attention, arrive on our screens the very instant they are observed, making the vast, distant asteroid belt feel as close as the device in your pocket. The Osiris-Rex mission to asteroid Bennu stands as a powerful proof of concept for this silent cartography. This ambitious venture sent a single, school bus-sized spacecraft on a multi-year journey to orbit, map, and ultimately touch down on the small, diamond-shaped asteroid. The data it returned was spectacular, revealing a world not of solid rock, but a loose rubble pile constantly shedding material into space. Yet this monumental achievement also highlighted the inherent limitations of a singular, complex explorer. Osiris-Rex was forced to spend months in a careful orbital dance, painstakingly building its maps piece by piece, its singular perspective requiring immense time and fuel to characterize the entire surface. The critical task of finding a safe touchdown site, free from treacherous boulders, became a global effort that consumed vast amounts of mission time. Now envision that same mission powered by a beacon swarm. Instead of one set of eyes, 1,000 microscopic observers blossom into a cloud around Bennu. They do not map the asteroid sequentially, but all at once. The entire surface, every crater and every boulder, is characterized in days, not years. The search for a safe sampling site is not a prolonged analysis, but an instantaneous consensus from a network that has already touched every square meter. And the mission's legacy would not end with a single sample grab. The swarm would remain, a permanent sentinel network monitoring Bennu's erratic spin and its habit of ejecting particles, providing a living, breathing understanding of a dynamic world long after a single spacecraft had departed. This comparison is not a critique of a past triumph, but a glimpse into a new paradigm. It demonstrates with concrete data how a distributed sensor network can achieve in a heartbeat what a solitary giant accomplishes through a long and costly campaign. The map of Bennu would shift from a static photograph in a mission archive to a real-time data stream, a dynamic portrait of an active asteroid. This case study solidifies the beacon's ultimate promise, transforming our approach from episodic visits to persistent presence, turning single points of knowledge into an ever-expanding web of cosmic awareness. This very silence, this ghost-like presence in the void, forces us to confront a difficult new reality. The ability to map a celestial body without leaving a trace is a power that carries profound ethical weight. We are entering an era of passive reconnaissance, a form of observation so discrete it is akin to placing undetectable surveillance cameras across the entire solar system. The core technical principle of the beacons, their near invisibility to all but their intended quantum receivers, is both an engineering triumph and a future source of immense diplomatic tension. Imagine a scenario where a corporation, under the flag of one nation, silently deploys a beacon swarm to a resource-rich asteroid that another nation has publicly claimed for its own. The first entity gains a complete three-dimensional map of every mineral deposit and structural flaw, a total information advantage, all without the other ever knowing the asteroid has been characterized. This is not a hypothetical conflict from a science fiction novel. Right now, international space lawyers and policy makers are struggling to draft protocols for exactly this situation. The foundational treaties of space law, written in an age of simple satellites and flags on the moon, are woefully unprepared for the age of microscopic sensor dust. They declare that celestial bodies cannot be claimed by sovereign nations, but they say nothing about the data gathered from them. Does a perfect, secret map of an asteroid constitute a de facto claim? Is it ethical to gain such a comprehensive understanding of a world that, by international law, belongs to all of humanity while sharing none of that knowledge? The beacons themselves have no allegiance, they are mere tools, but the silent maps they draw will become the most valuable secrets in history, forcing us to decide if the final frontier will be a commons of shared discovery or a new arena for silent, invisible competition. This silent cartography is not driven by curiosity alone, but by a powerful economic engine. The maps these beacons create are the modern equivalent of the geological surveys that defined the gold rushes of old, transforming a landscape of anonymous wilderness into a grid of characterized claims. The most valuable resource they identify is not gold, but water. Asteroids rich in water ice become the celestial gas stations and bottled water companies of the future. Water can be split into hydrogen and oxygen, the fundamental components of rocket fuel, enabling spacecraft to refuel without the immense cost of launching propellant from Earth's deep gravity well. This single capability makes the entire solar system more accessible. Beyond water, the beacons pinpoint veins of platinum group metals, essential for everything from catalytic converters in cars to the circuitry in the device you are using right now. They locate vast, solid loads of iron and nickel, the raw materials for constructing habitats and factories in space itself. This precise identification is what de-risks the astronomical gamble of asteroid mining. An investor is no longer funding a mission to a mysterious rock, hoping for a lucky strike. They are financing an extraction operation at a specific, pre-surveyed asset with known composition, known mass, and a known structural integrity. This data is the bedrock, the very foundation, upon which a self-sustaining off-world economy will be built. It is the crucial first step in moving our species from an Earth-reliant existence to a truly spacefaring civilization, where the resources for growth and survival are harvested from the infinite landscape above, rather than the finite one below. The same network that quietly plots the future of our economy also stands guard against our ancient past. While the maps point to incredible wealth, they also illuminate potential pathways of destruction, transforming the beacons into a global early warning system of unprecedented power. Their most critical function in planetary defense is not just finding a dangerous asteroid, but finding it early. With decades or even centuries of advance notice, a threat that could end civilizations becomes a manageable orbital correction. The beacons achieve this through persistent surveillance, by constantly tracking the subtle wobbles and orbital paths of thousands of near-Earth objects. They build a predictive model of the solar system's small body population with stunning accuracy. They are not just taking a snapshot, they are watching the traffic flow in slow motion, identifying any object whose future path might, through a complex gravitational dance, eventually intersect with our own. But early detection is only half the battle. Knowing a mountain is coming is useless if you do not know how to move it. This is where the silent maps reveal their second, more profound purpose. To successfully deflect an asteroid, you need to know precisely what you are pushing against. A solid nickel-iron asteroid would require a different kind of nudge than a loose rubble pile, which behaves more like a fluid bag of rocks. The beacon swarm provides this essential intelligence. Its composite data reveals the exact mass distribution, the internal structure, and the precise location of the object's center of gravity. With this knowledge, engineers can calculate the optimal point to attach a steady, low-thrust engine or to detonate a device, ensuring the force applied translates into a clean, predictable change in trajectory, not a chaotic fragmentation that could create a shotgun blast of debris. In this role, the tiny, silent mappers become the most vital guardians our planet has ever known. Their unblinking watch ensuring that the story of humanity does not end with the same sudden impact that may have begun it. This constant whisper from the void generates an ocean of raw information, a deluge of data that would drown any conventional system. Managing this flow requires a computational backbone of staggering scale and intelligence back on Earth. The signals from millions of beacons feed into vast server farms where artificial intelligence and machine learning do not merely store the information, they learn from it. These are not passive databases, they are active digital minds. Sophisticated algorithms are trained to recognize subtle patterns that would be invisible to any human analyst. They can look at the spectral data from 1,000 different points on an asteroid and instantly identify the unique chemical fingerprint of a platinum vein, distinguishing it from a dozen other similar-looking metals. They can analyze the minute gravitational wobbles of a celestial object and predict its orbital path not just for years, but for centuries into the future, identifying potential threats long before they become urgent. This digital brain is in a constant state of refinement. With every new data point received, the models become sharper and more accurate. They cross-reference findings from different asteroid swarms, uncovering deeper truths about the formation and composition of our solar system. The ultimate output is not a static map filed away in an archive. It is a living, breathing digital twin, a dynamic simulation of the solar system's entire small body population. This virtual model allows scientists and engineers to run simulations, to test theories, and to foresee future events with a clarity that was once the realm of pure fantasy. It transforms the chaotic, raw data of the cosmos into a stream of pure, actionable intelligence, a crystal ball built not from magic, but from the silent, collective observation of a billion tiny eyes. The brutal environment of space guarantees that some beacons will fall silent. Radiation, temperature extremes, and microscopic dust impacts are relentless. This inevitability is not a design flaw, but a core consideration. The network is built on a foundation of redundancy. Each individual unit is statistically insignificant. If 10% of a swarm fails, the map does not simply vanish. Its resolution might become slightly grainier, like a digital image losing a few pixels, but the overall picture remains perfectly clear and functional. The mission continues uninterrupted because the collective intelligence is distributed, not centralized. The loss is absorbed by the swarm, a silent testament to the power of numbers. Yet the most advanced concepts push this resilience even further. Theorists envision a second generation of swarms that include specialized mechanic beacons. These units would be slightly larger, equipped with microscopic manipulator arms, fine-tipped tools smaller than a needle's point. Their sole purpose would be to tend to their siblings. A mechanic beacon could gently brush obstructive dust from a neighbor's solar panel, restoring its power supply. It could perform a delicate nudge to realign a communication antenna that has been knocked a fraction of a degree off its optimal angle. These are not complex overhauls, but simple, life-extending repairs. This emergent capability for self-healing transforms the network from a temporary sensor array into a persistent entity. Its operational lifetime stretches from a few planned years to potentially decades of continuous service. The silent maps they generate are no longer static documents, but living chronicles, perpetually updated and verified, ensuring that our understanding of the cosmos remains as current and reliable as the unblinking stars themselves. The most elegant solutions for navigating the void were not invented in a laboratory, but have been field-tested by nature for millions of years. The collective intelligence of a beacon swarm is a direct echo of biological phenomena we can observe all around us. Consider a massive school of sardines, a shimmering, fluid cloud in the ocean. When a predator strikes, there is no central fish shouting orders. Instead, each fish follows a handful of simple rules like stay close to your neighbors, match their speed, and move away from any sudden disturbance. From this local, decentralized coordination emerges a breathtakingly complex and adaptive group behavior that protects the whole. This exact principle is what engineers have codified into the algorithms governing the beacons. There is no master controller dictating every movement. Each unit operates on a limited set of instructions, like maintain a minimum distance from your neighbors, share your sensor data, and move towards areas of unknown composition. The sophisticated map, the efficient coverage of an irregular surface, all of it emerges from the bottom up, just like the fish school evading a shark or an ant colony, efficiently foraging for food without a single command ant. This biomimicry extends far beyond simple coordination. For energy harvesting, engineers are designing microscopic structures that mimic the process of photosynthesis, aiming to capture and convert solar energy with the same quiet efficiency as a leaf. The very physical form of the beacons often incorporates fractal patterns, those intricate, repeating shapes found in ferns, snowflakes, and coastlines. These patterns provide incredible structural strength while using the absolute minimum amount of material, a critical advantage when every microgram launched into space carries a cost. It is a profound realization that the most robust and efficient models for exploring the vast, alien cosmos are being discovered right here at home, written into the DNA of life itself. The final duty of these tiny mappers is to become a permanent part of the cosmic landscape they help define. The silent maps they generate do not simply fade away when their power dwindles. This data, the complete portrait of an asteroid, is transmitted back and integrated into a permanent celestial library, a growing archive of our solar system that will be passed down through generations. It becomes a foundational record, allowing a scientist 100 years from now to study the precise composition of an asteroid that was mapped before they were born, or an engineer to plan a mining mission to a resource that was characterized decades prior. The beacons themselves, however, face a more poetic fate. Some, with a little power remaining, will not die. They will enter a deep hibernation mode, shutting down all but their most basic systems to become dormant markers, scattered like cosmic breadcrumbs across the surface. A future mission arriving years later could send a simple wake-up signal, and these silent sentinels would stir back to life, offering their historical data and serving as pre-positioned navigation aids. Others, whose thrusters are spent and batteries nearly empty, perform one last act of service. With their final joule of energy, they might fire a cold gas thruster to deorbit, casting themselves into the void to burn up as a fleeting, harmless meteor. Or, in a more deliberate finale, they could guide themselves to a controlled impact on the asteroid's surface. This final collision is not a death, but a last experiment. The tiny flash and seismic ripple created adds one final, crucial data point about the surface's hardness and density, a final whisper of information for the swarm to record. Their physical forms may be gone, but the map they carved endures, a timeless and silent gift to the future. This global rush toward the asteroids unfolds across two parallel and often conflicting stages. On one hand, you have the grand collaborative science led by agencies like NASA and the European Space Agency. These organizations are pioneering the open standards that allow a Japanese-built Hive ship to release a swarm of beacons using communication protocols developed in Germany, with the resulting data stream flowing into a public archive accessible to researchers in Brazil and India. This international framework is the bedrock, ensuring that the fundamental science of our solar system remains a shared human endeavor. Yet operating alongside this open consortium is a vibrant, aggressive private sector. Companies like SpaceX are slashing the cost of delivering Hive ships to the belt, while ventures like Astroforge treat the resulting maps not as public knowledge, but as corporate secrets more valuable than any patent. The data from their proprietary swarms is the new gold, locked away to guide their mining drones to the richest claims. This creates a fundamental tension. How do you build a cooperative, interoperable network when the most valuable pieces of information are deliberately walled off? The old treaties, drafted for a simpler era of space, are buckling under this pressure. They clearly state that no nation can claim sovereignty over the moon or an asteroid, but the law is silent on the data. Does a perfect, three-dimensional map of an asteroid's every mineral deposit constitute a de facto claim if it gives one entity an insurmountable head start? This is the new frontier of law, a debate happening in conference rooms at the United Nations, where diplomats are scrambling to define what ownership means in an age of silent, non-invasive reconnaissance. The race to chart the void is mirroring the great age of exploration, with corporate flotillas and international science vessels all deploying their silent, microscopic ships into the same cosmic ocean, all guided by the same revolutionary technology, but toward vastly different ends. This silent observation extends to a crucial, often overlooked principle: the profound lack of impact the beacons have on the worlds they study. While a traditional spacecraft might land with a shuddering crash, kicking up dust and potentially altering the very surface it came to analyze, these micromachines are designed as perfect ghosts. Their physical footprint is virtually non-existent. Many do not even make contact with the asteroid at all. Instead, they use their minute thrusters to maintain a stable hover, a delicate ballet just centimeters above the dusty regolith, mapping the surface without ever touching it. Their entire mode of perception is built around this non-invasive philosophy. The laser pulses and low-energy radio waves they employ for active sensing are so faint they leave no mark, gathering data without causing any contamination or change to the primordial rock. This leave-no-trace ethic is not merely an engineering preference, it is a scientific imperative. Asteroids are time capsules, pristine relics holding chemical clues to the formation of our solar system over 4 billion years ago. The moment you land a conventional probe and disturb the surface, you risk erasing those clues forever, mixing ancient dust with modern contaminants. The beacons allow us to read the book of our cosmic origins without tearing out any pages. They ensure these drifting mountains remain perfect, unaltered natural laboratories, even as we meticulously catalog the trillions of dollars in resources they contain. We can have both pure science and future industry because our method of seeing is also a promise to preserve. The silent cartography of today is already giving way to the autonomous architects of tomorrow. These are not just incremental upgrades, but fundamental reimaginings of what a beacon can be, transforming them from passive observers into active participants in the cosmic landscape. The first major leap involves giving beacons the ability to feed themselves. Next-generation designs include microscopic chemistry labs capable of in-situ resource utilization. Imagine a beacon that lands on a patch of water ice in a permanently shadowed crater. Using minuscule amounts of its own stored energy, it could power a tiny electrolysis cell, splitting the water molecules into hydrogen and oxygen, which it then liquefies and stores as its own propellant. This single capability would revolutionize mission longevity, allowing a swarm to refuel itself from the very asteroid it is mapping, hopping from one resource-rich site to another without ever waiting for a resupply from Earth. Another evolutionary branch focuses on intelligence. The current model sends raw data home for processing, but future processor beacons would carry more powerful, specialized chips. These units would act as local analysts, sifting through the immense data stream from their neighbors. Instead of transmitting trillions of raw spectral readings, a processor beacon could identify the signature of a platinum group metal itself and send back only the confirmed finding and its precise coordinates. This condenses a flood of information into a single, valuable sentence, dramatically reducing the communication burden and allowing the network to make its own discoveries in real time. But the most profound concept on the drawing board is that of self-replication. This is the ultimate expression of autonomy, where a single hive ship could seed an entire asteroid belt with a network that grows exponentially. The design is staggering in its ambition. A primary beacon would land on a metal-rich asteroid. It would then use a focused energy beam, perhaps a microscopic laser, to vaporize and sinter regolith dust, effectively three-dimensional printing the internal components for a new beacon. It would harvest trace elements from the rock to create new circuitry and use locally mined water ice to create propellant for its offspring. The first copy would be slow, perhaps taking a year to complete. But then there would be 2 printers, then 4, then 8. Within a decade, a single seed could spawn a swarm of millions, all built from the asteroid itself, all ready to launch toward the next unexplored world. This is no longer just mapping the void. It is learning to build with it, creating an ever-expanding web of awareness that could one day touch every corner of our solar system. This vast library of cosmic data holds little value if it remains locked away in supercomputers. The 12th principle driving this silent cartography is a radical commitment to public engagement, a deliberate effort to democratize the very data these beacons collect. Imagine a digital portal accessible from any personal computer or public library terminal that opens a window directly to the asteroid belt. You are not looking at a static artist's rendering, but a fully interactive, three-dimensional model of a real, mapped asteroid, perhaps one that could one day fuel a spacecraft or require deflection. You can spin the irregular, potato-shaped world with your finger, zooming in to see individual craters named by schoolchildren, and toggle different data layers that appear like transparent overlays. One layer might paint the surface in vivid colors to show concentrations of water ice, glowing blue in the permanent shadows of polar craters. Another could highlight rich deposits of platinum group metals in shimmering gold. This is not a game, it is the real, unedited map the same day to a mining corporation or a planetary defense team would use. This radical transparency serves a profound purpose. It demystifies the often abstract and distant concepts of space mining and planetary defense. When you can personally explore an asteroid and see for yourself the potential resources and the orbital path that might one day bring it near Earth, these grand endeavors shift from science fiction headlines to tangible, understandable realities. This open access does more than just inform, it inspires. A student in a classroom can become the first person to spot a unique mineral formation on a distant rock, fostering a sense of ownership and wonder that no textbook could ever provide. By inviting everyone to explore the cosmos from their own screen, the beacon projects are mapping more than just asteroids. They are carefully charting a new, inclusive relationship between humanity and the final frontier, transforming a passive global audience into an active, participating civilization. This transformation marks a fundamental change in our cosmic ambitions. We are no longer just visitors peeking through the keyhole of the solar system. With the silent maps provided by the beacons, we are becoming superintendents of a vast extraterrestrial domain. The age of pure exploration, of sending a lone probe for a brief, glorious flyby, is giving way to the age of administration. This is the philosophical shift at the heart of the entire endeavor. It is the difference between a nomadic explorer crossing a new continent for the first time, marveling at its untouched wilderness, and a settled civilization that follows, surveying the land, laying down roads, and managing its resources for the long term. The beacons are the surveyor's stakes and the land deeds of this new frontier. Their persistent, quiet watch turns the chaotic and unknown void into a managed, navigable, and economically integrated part of our human environment. This is not a loss of wonder, but an evolution of responsibility. We are learning to read the cosmic ledger, to understand the balance of resources and risks in our celestial neighborhood. It raises a deep, reflective question for all of us. What does it mean for a species to grow up, to shift from simply wandering the cosmos to consciously tending to it? This is the quiet promise and the profound weight of the maps being drawn right now, in the darkness between the worlds. The sheer scale of the beacon network makes direct human oversight a physical impossibility. Millions of autonomous units cannot be micromanaged from a control room on Earth, where a single command can take over an hour to reach its destination. This is where the silent captain of the fleet takes command, a distributed artificial intelligence woven into the very fabric of the swarm. This eye is not a single, monolithic mind, but a layered intelligence. A simple, robust eye operates within each individual beacon, handling its basic navigation and immediate survival. A far more sophisticated system resides in the orbital relay stations and ground-based data centers, processing the collective stream of information. This hierarchy of intelligence allows the network to function with a resilience and efficiency that would be impossible under human direction alone. The system's primary role is constant, vigilant anomaly detection. It monitors the endless stream of data, looking for patterns and, more importantly, for breaks in those patterns. If a single beacon on the far side of an asteroid registers a localized, intense magnetic field where none was predicted, the ground-based AI does not wait for a human operator to notice. It instantly tasks a cluster of 12 nearby beacons to break from their standard mapping routine. Their new, autonomous mission is to converge on that anomaly, forming a dense, impromptu sensor array to take simultaneous readings from multiple angles. This spontaneous coordination happens in seconds, a localized investigation triggered and executed entirely by the machine mind. This autonomy extends to the fundamental safety of the swarm itself. The AI manages a constant, delicate dance of collision avoidance, calculating the trajectories of every beacon in relation to its neighbors and to the asteroid's own irregular topography. It can predict potential conjunctions, moments where two units might drift too close, and issue minute course corrections to their micro-thrusters long before a problem arises. It also handles dynamic task prioritization. If the primary mission is mineral mapping, but the swarm suddenly detects a new vent of gas erupting from the surface, the AI can instantly reassign a portion of the fleet to track the plume's composition and dispersion, all while the majority continues its original work. This level of independent decision-making is not a luxury, it is the bedrock of the network's functionality. It allows the entire system to react to its environment in real time, to heal itself from internal failures, and to pursue unexpected discoveries the moment they appear, making the silent map not just a pre-programmed survey, but a living, learning document of a dynamic cosmos. Every grand vision must face the cold, hard light of practical reality. The blueprint for this silent network is undeniably elegant, but skeptics rightly question whether it can survive the brutal economics and physics of deep space. The most immediate objection is the staggering price tag. How can we possibly afford to manufacture and launch not just millions, but ultimately trillions of these microscopic explorers? The answer lies not in building them like spacecraft, but like computer chips. The same photolithography techniques that can print 1 billion transistors onto a sliver of silicon are being adapted to print entire beacons in vast parallel batches. This is not assembly, it is replication. A single production facility could output millions of units per day, driving the individual cost down from thousands of dollars to mere pennies. The launch cost itself is being tackled by the rise of dedicated, minimalist hive ships. These are not multi-purpose science vessels, but disposable freight trains for the void, designed for one job, to carry a massive payload of beacons on a one-way trip and then scatter them like cosmic seed. When you combine ultra-cheap manufacturing with ultra-efficient delivery, the financial model flips. The cost of characterizing an entire asteroid drops from billions to perhaps millions, a price that falls squarely into the budget of a mid-sized corporation, not just a superpower nation. Then there is the question of the quantum link, the very nervous system of the swarm. Can these delicate, entangled particles really survive the violent radiation and jarring temperature swings of interplanetary space? This is not a theoretical debate, it is an active engineering battlefield. Inside laboratories like the MIT Space Nanotechnology Lab, prototypes are being subjected to a special kind of torture test. They are blasted with proton beams to simulate solar radiation, flash frozen in cryogenic chambers, and shaken on vibratory tables that mimic the violent launch atop a rocket. The goal is not just to see if they break, but to discover precisely how they fail, and then redesign them to be stronger. Early results are promising, pointing to new, radiation-hardened materials and self-correcting circuitry that can repair minor quantum decoherence on the fly. The technology is not yet perfect, but it is progressing from a laboratory curiosity into a space-worthy component. Perhaps the most unnerving prospect is that of a cascading failure. What if a software bug or a localized radiation burst causes one beacon to malfunction, and its errant behavior spreads like a digital virus through the entire swarm, collapsing the collective mind? This risk is taken seriously, and the solution is baked into the core algorithms. The swarm's intelligence is decentralized for a reason. It has no central brain to infect. Fail-safes are programmed at the most basic level. Each beacon is designed to be inherently skeptical of its neighbors. If one unit starts broadcasting impossible data, like a sudden jump in location or a physically improbable sensor reading, the surrounding beacons do not blindly obey. They isolate the erratic unit, marking its data as untrustworthy and reorganizing the network around the gap. It is a digital immune system. The swarm is designed to lose members gracefully, to sacrifice a few to save the whole. This robust, anti-fragile nature is what turns a potential weakness into a core strength, proving that the greatest hurdles often forge the most resilient solutions.